For decades, communicating with submarines and underwater vehicles has been one of the most challenging problems in military and scientific operations. Radio waves, which power our modern wireless world, simply cannot penetrate seawater beyond a few meters. This fundamental limitation has created what military strategists call the underwater communication gap, a persistent blind spot that has shaped naval doctrine for generations. But now, a remarkable breakthrough in quantum physics might finally bridge this gap. Today, we'll explore how Chinese researchers have achieved quantum communication through 3.1 kilometers of seawater, potentially revolutionizing submarine operations, underwater infrastructure, and our understanding of the oceans. The physics behind underwater communication challenges is straightforward but unforgiving. Seawater contains dissolved salts that create a conductive medium, causing electromagnetic waves to attenuate rapidly. This means traditional radio waves, the backbone of our wireless world, become useless just a few meters underwater. For decades, submarines have been forced to either surface or deploy antennas near the surface to communicate, creating vulnerability windows that compromise their stealth capabilities. Current underwater communication relies primarily on acoustic signals, or sonar, which travel slowly, about 1,500 meters per second compared to radio waves 300 million meters per second in air. These acoustic signals are vulnerable to ambient noise and can be easily intercepted. Another option has been extremely low-frequency radio waves, or ELF systems, but these require massive shore-based transmitters and can only send a few characters per minute, making them suitable only for the most basic commands. These constraints have remained essentially unchanged since World War II, creating a persistent blind spot in global communication networks that has fundamentally shaped how navies operate worldwide. To understand the breakthrough, we need to grasp the basics of quantum entanglement, what Einstein famously called spooky action at a distance. When two particles become entangled, their quantum properties become linked in such a way that the state of one particle instantly influences the state of the other, regardless of the distance separating them. This isn't just theoretical. It's a proven phenomenon that defies our classical understanding of physics. In quantum communication, we can use this property to create unhackable communication channels. By generating pairs of entangled photons, particles of light with these linked properties, and sending one photon through a medium while keeping its partner at a base station, we can establish a secure quantum key distribution, or QKD channel. Any attempt to intercept or measure these photons would disturb their quantum state, immediately alerting the communicating parties to the presence of an eavesdropper. This makes quantum communication theoretically unhackable, a holy grail for secure communications. In findings published in the journal Physical Review Applied, researchers led by Dr. Xiaowei Bao achieved something remarkable. They successfully transmitted quantum encrypted information through 3.1 kilometers of seawater in the South China Sea. This isn't just an incremental improvement, it's a 1,000-fold increase over previous experiments that were limited to just a few meters in laboratory tanks. The team generated entangled photon pairs and sent one photon through a fiber optic cable along the seabed while keeping its entangled partner at a shore station. By measuring the quantum state of the underwater photon and comparing it with its entangled partner, they established a secure quantum key distribution channel. What makes this achievement particularly impressive is how it overcomes the significant problem of photon loss and decoherence in water. The researchers developed a new protocol called Adaptive Quantum State Correction, or AQSC, which continuously monitors the quantum channel's characteristics and applies real-time corrections to the entangled photons. This sophisticated feedback system measures how the underwater environment affects quantum states and then pre-compensates for these effects at the source. The results speak for themselves. Dr. Bao's team achieved a quantum bit error rate of just 3.8%, well below the 11% threshold required for secure quantum key distribution. The military implications of this breakthrough cannot be overstated. Submarines represent one of the most important strategic assets in modern naval warfare, primarily because of their stealth. Their effectiveness depends entirely on remaining undetected, yet they must periodically communicate with command centers. This creates what naval strategists call the communicate or hide dilemma, a fundamental paradox that has defined submarine operations since their inception. Every time a submarine needs to receive orders or transmit intelligence, it must compromise its stealth to some degree. This quantum communication method could potentially allow submarines to receive secure communications without surfacing or deploying vulnerable antenna buoys, fundamentally changing the strategic equation. Naval strategists have long sought what they call continuous communications dominance, maintaining constant contact with underwater assets without creating vulnerability. Quantum underwater communication could finally resolve this strategic paradox. According to defense analysts, this technology potentially eliminates the fundamental dilemma that has defined submarine operations for over a century. This would represent not just a technical advancement but a paradigm shift in naval warfare doctrine. Beyond military applications, this technology could revolutionize underwater internet infrastructure. The global internet relies on a vast network of undersea fiber optic cables that are vulnerable to physical damage and surveillance. Quantum-secured links could provide unhackable backup channels for these critical communication arteries. The oil and gas industry, which operates extensive underwater infrastructure, stands to benefit enormously from secure, high-bandwidth communication with subsea equipment. Companies like BP and Shell currently spend millions annually on remotely operated vehicles that require physical tethers for control. Quantum communication could enable truly wireless operation of these vehicles, dramatically reducing costs and expanding operational capabilities. This would transform how we install, maintain, and monitor underwater infrastructure, from oil platforms to wind farms to desalination plants. The potential cost savings and efficiency improvements are substantial, potentially reducing the price of everything from energy to internet access. And while the current data transmission rate is modest, about 0.2 kilobits per second, sufficient for text messages and critical commands but not for video, researchers are already working to increase this bandwidth substantially. Perhaps the most exciting applications for many scientists lie in environmental monitoring. Climate scientists tracking ocean temperatures, currents, and marine ecosystems could deploy networks of quantum-linked sensors that transmit data securely and efficiently. Our understanding of deep ocean processes is severely limited by data transmission constraints, but quantum communication could enable real-time monitoring of abyssal ecosystems that remain largely unexplored. This could prove crucial for tracking marine biodiversity loss, monitoring the impacts of deep-sea mining, and understanding the ocean's role in climate change. The oceans are our planet's largest carbon sink and heat reservoir, yet we have remarkably limited data about processes occurring below a few hundred meters depth. Quantum-linked sensor networks could transform oceanography from a field reliant on periodic sampling to one with continuous, real-time data streams from the deepest parts of our oceans. This would revolutionize climate modeling, fisheries management, and marine conservation efforts. The technology could also transform disaster prevention systems. Tsunami early warning networks, which rely on pressure sensors on the ocean floor, currently face significant communication delays. Quantum-linked sensors could provide instantaneous alerts, potentially saving thousands of lives in coastal regions vulnerable to these devastating natural disasters. Despite this breakthrough, several technical challenges remain before quantum underwater communication becomes widely deployed. The system still requires fiber optic infrastructure on the seabed, which limits its flexibility and increases deployment costs. Researchers are exploring free space quantum communication through water, which would eliminate the need for physical cables, but this approach faces significant hurdles. Temperature fluctuations, turbidity, and marine biofouling present obstacles to long-term deployment in open ocean environments. The quantum receivers also require cryogenic cooling, making them bulky and energy-intensive, a particular challenge for submarine applications where space and power are at a premium. The current data transmission rate of 0.2 kilobits per second is sufficient for text messages and critical commands but falls far short of what would be needed for video or large data transfers. The research team is now working to extend the communication distance to 10 kilometers and increase this data rate substantially. These are significant engineering challenges, but the proof of concept has been established. The question is no longer if quantum underwater communication is possible, but rather how quickly it can be refined and deployed at scale. This breakthrough comes amid increasing international competition in quantum technologies, with China, the United States, and the European Union all making substantial investments in quantum research. The underwater application demonstrates how quantum advances can have immediate strategic value beyond the commonly discussed areas of computing and cryptography. China's achievement in underwater quantum communication represents a significant advance in what many are calling the quantum race. the international competition to develop and deploy quantum technologies with military, economic, and scientific applications. The United States has invested billions in the National Quantum Initiative, while the EU has its quantum flagship program with similar funding levels. These investments reflect the understanding that quantum technologies represent not just incremental improvements but potentially revolutionary capabilities that could reshape military balances, economic competitiveness, and scientific understanding. The country that leads in quantum technology development may gain significant advantages across multiple domains, from unhackable communications to advanced computing capabilities that could break existing encryption standards. This underwater quantum communication breakthrough demonstrates that these aren't distant theoretical concerns but rapidly emerging capabilities with immediate practical applications. Dr. Bao's team has effectively created a new paradigm for underwater communication that doesn't fight against the physical limitations of seawater but instead exploits the counterintuitive properties of quantum mechanics to bypass them entirely. In doing so, they've demonstrated that the most profound technological breakthroughs often come not from incremental improvements to existing systems, but from fundamentally new approaches based on a deeper understanding of nature's underlying principles. This represents a philosophical shift in how we approach underwater communication. For decades, engineers have tried to overcome the limitations imposed by seawater's conductivity through more powerful transmitters, more sensitive receivers, and clever signal processing. These approaches have yielded modest improvements but have never solved the fundamental problem. Quantum communication takes an entirely different approach. Rather than trying to force conventional electromagnetic waves through a resistant medium, it leverages the bizarre properties of quantum mechanics to establish communication channels that operate according to different physical principles entirely. As quantum technologies mature, we may soon see a new era of underwater communication that is more secure and fundamentally different from anything that has come before. The ocean depths, which cover more than 70% of our planet yet remain largely inaccessible to our information networks, may finally be integrated into the global communication infrastructure. The breakthrough in underwater quantum communication represents one of those rare moments when theoretical physics transforms into practical technology with far-reaching implications. By harnessing the spooky properties of quantum entanglement, researchers have begun to solve a problem that conventional physics deemed nearly impossible: reliable, secure communication through seawater. This achievement could fundamentally transform submarine operations, underwater infrastructure management, and our ability to monitor and understand the oceans that cover most of our planet. The military implications alone would reshape naval strategy that has remained largely unchanged since World War II. Beyond defense applications, this technology promises to connect the last great communication frontier on Earth, the ocean depths, to our global information network. As researchers work to extend the range, increase bandwidth, and overcome remaining technical challenges, we stand at the threshold of a new era in underwater operations. The quantum communication breakthrough reminds us that the most significant technological advances often come not from incremental improvements to existing systems, but from fundamentally new approaches based on deeper understanding of nature's principles. In bridging the underwater communication gap through quantum physics, we're witnessing not just a technical achievement but a conceptual leap that could ripple across multiple fields for decades to come. Thanks for watching. Please like, subscribe, and hit the bell icon for updates. Your feedback is appreciated. We hope to see you again.